So we can get started with the agenda, and the topics that I plan to cover are listed here. We'll briefly go over supervised versus unsupervised learning. There was a question, so I'll briefly talk about that. And then we'll look into some examples of ensemble methods. Like ensemble is like putting together many things. So we'll talk about bagging, random forest, and extreme gradient boosting methods. We will look at both examples, one regression tree examples using Boston housing data, and then also classification tree examples using CTG data. So these methods can be applied for both situations, whether you are dealing with regression problem, regression meaning your y variable is numeric, and classification problems where your y variable is a factor variable. So it may have 2, 3, or more classes. These methods are mainly machine learning methods, and machine, as you know, refers to computers. So we do a lot of work on computers because we can get repetitive things done very quickly. So that's the idea about machine learning using computers, and learning obviously takes place using data. So using computers and data to develop models. But these methods are classified very broadly into two categories. One is supervised and other is unsupervised learning. So supervised learning in a very simple way is a situation where the goal is to predict a single target or outcome, and this target value is known. So we are talking about your variable y, which is the dependent variable. So this variable y is a dependent variable, and the methods that we use belong to mainly two categories: classification, when this y is factor, and regression when it is numeric. So those are the two situations. And actually machine learning people also give another name to classification plus regression. So when you are doing both, so that's what is called predictive analytics. And unsupervised learning, the goal is to segment your data into meaningful segments or groups. And the idea is to detect patterns. And there's no y variable here, no target. So we are only dealing with, you can say, independent variables like x1, x2, x3, and there's no y variable. And some of the popular methods include association rules that you see applied to so many situations. For example, when you watch a movie on Netflix, and next time you go there, it will make you some suggestion. So based on the previous patterns by various people, it may suggest you that you may like this movie because you watched that movie. Or if you are looking to buy a book on Amazon, it may also give you a suggestion that, like, those people who bought this book, they also bought this other book. So all those things are basically based on association rules, also called as market basket analysis. So people analyze that data and see what things go together and then implement that. And under unsupervised learning, we also have methods for data reduction. Especially with a lot of data, there are two situations that can emerge. We may have a situation where we have a lot of independent variables, 500 or 1000 or 1500 or even more. So a lot of x variables, lot of like independent variables. So how do you reduce dimension of that data? So for that, there are unsupervised learning methods that can help. And one popular method is principal component analysis. So instead of having to deal with 1500 variables, if you do principal component analysis, it can reduce the number of variables you deal with significantly. Like you may have to deal with maybe 5 or 10 principal components, which are linear combination of all those 1500 variables, but they retain like a lot of variability within them, and you don't lose too much. On the other hand, if you have lot of rows, like millions and millions of rows of data, and you want to reduce that, then there are clustering methods like k-means clustering and so on. So there are several methods which are very popular with unsupervised learning for data reduction and exploration, and also for data visualization. But in this class, we have looked more towards classification and regression problems. So we started with simple linear regression, went on to multiple linear regression, then logistic regression, and then regression trees and so on. Now, how these methods work in real world? So there are two stages. First stage is model development. So what we do there is we work with data. Sometimes data is not available, we have to collect it, or sometimes data is available but it has to be organized in certain way. So there's a lot of pre-processing. So as a data scientist, sometimes you may have to spend a lot of time just preparing the data. So it may have missing values, it may have a lot of issues, like real world data is messy, as you might have seen in some of your projects. So just preparing that data in a right way before a model can be developed itself is a big task. And a lot of data scientists spend almost like 60-70% of their time just doing data preparation. But once the data is ready, then what we are seeing, especially when we have a lot of data, we partition that data into train and test. And then we use that train data to develop a model. Like in this example, I'm showing a tree model, but it could be any other model. It could be logistic regression, it could be multiple linear regression. So basically, we come out with a model and we use test data to assess performance of the model, like how that model is doing. And once after lot of iterations, let's say we are happy with the outcome and we have the result, and we want to deploy that model, we want to implement it. So now that's another stage. So there are a lot of issues that may crop up while developing the model. Going through the entire process is sometimes not very straightforward. So there are a lot of issues. You may have to make a lot of assumptions. You may have to do a lot of data processing, pre-processing, switching from one model to the other model. But once you are ready with that, now model deployment is again a whole new world. So it may have its own issues, its own challenges, its own problems. It's not that we develop the model and our job is done. So model deployment may be very tricky in some situations. I worked with some companies for consulting when they were developing machine learning models, and I have seen firsthand like what kind of problems can come. We don't go into the details of that. Obviously, like while doing the project, you may come across few things, but once you have a model ready, once you want to deploy, so in this case, this model was developed to classify a new applicant as admit or not admit. So now you have a new application. So you use the model, and then the model tells you something. So it says reject probability is 0.59, accept is 0.40, and let's say your cutoff is 50%. So your decision based on this model is going to be reject. So broadly, this process of developing models goes into like two phases. One is development and other is deployment. coming to regression tree examples using Boston housing data that we have seen earlier also. This is a picture of regression tree. So why I am calling this as a regression tree model here? Because the y or the response variable is numeric. So in this data, Boston housing data, if you recall, our response variable is MEDV, so median house price. So we developed a regression tree, but with regression tree, if you have different random splits, so if you have 50-50, 50% is training and 50% is testing with one set dot seed, and then you again do 50-50 with another seed, you may find that your tree model gives a very different result. So I have used three different splits. One is in black color, another one red, and the third one is green. LSTAT is your independent variable. So I have used the most important variable on the x-axis because we cannot plot too many variables. So I just use the most important. And on the y-axis, we have the response. So using the tree model for any given LSTAT, the value of MEDV based on the tree model can be predicted using these black dots for one model. But if you have same data and you again split the data 50-50 and create a tree model, you can see there is a big gap now. So earlier we were saying that for a given LSTAT value here, prediction is somewhere around $17,000, and suddenly it drops to about $12,000 or $13,000. And then you have another one, same data and but new tree model, and it predicts 10,000 now. So you can see at one level your prediction changes so much even with the same data. And you can see similar pattern occurring across different values actually. So decision trees suffer from high variability in results. So that's one of the features of a decision tree, that you create another tree and the results could be very different. So that's a big difference, 10,000 versus 17,000. So 7,000 variability just at one level. So that's a problem. I read a story, or I heard a story where there was an old man who was dying and he had four children, and they used to fight among themselves a lot. So before he thought, I die, I want to at least convey some message to them because this world is a difficult place to live and they should live together. So he asked them to bring a stick each and asked them to break that stick. And all four young boys were very strong, very healthy. They were easily able to break that stick. So then he asked them to bring sticks and like tie them with a rope, and then asked them to try and breaking it one by one, and none of them were able to break it. So the moral of the story was that if you are together, you will be much stronger. And that's what is actually the idea behind ensemble methods. So just as an example, if we are doing weather forecast and you have a reality at the top in different columns, and let's say you make a prediction using one tree, and you can see some places there is a mismatch, basically saying predictions are not accurate. So in reality there was a rain, but prediction was that there is a sunshine. Same thing with many individual tree methods. But if you combine everything, if you take, for example, the rainy one is like majority 4 out of 5. So if you use that as a prediction, same thing for all other days, you'll notice that you are much more accurate. So that's exactly the idea behind combining results from various trees instead of depending on one tree. And you may also recall central limit theorem, where you have a normal distribution for any variable, random variable x. But if you take a sample of size maybe 30 many times and create a normal distribution of those x bars, the means, not the individual values, but the means, you'll find that that normal distribution is very thin. It has low variability. As you increase the sample size, variability decreases. So that's the idea behind ensemble methods. So one of the popular methods is called bagging. Now why it is called bagging? It takes B from Bootstrap and then remaining part from aggregating. So the method is actually Bootstrap aggregating. What is Bootstrap? So Bootstrap sampling is random sampling with replacement. We had done that earlier also, where we take samples, but we are taking samples with replacement. So how does this work? So let's say you have a data and you split that data into training data and testing data. So because we'll be making models on training data, so you take a training data and then take a bootstrap sample from this training data and call it data 1. When you take a sample from the training data which is with replacement, what can happen is that some observations, some cases, like if it is housing data, so some houses may be selected more than once. So because you may be selecting a house, replacing it back, and then again if you take a sample, then just by chance it may get selected. So in this data, you may have some data points which are repeated, and it can also happen that many data points are not even selected once. So that also can happen with the first data. And then you take another bootstrap sample from the training data independent of the first one. So whatever happened with data 1, it happened. Now with data 2, you just don't worry about anything else. Again, dip into your training data and take bootstrap sample with replacement. So basically data 1 and data 2 are independent of each other. So it's not, data 1 doesn't dictate what shape data 2 will take. So data 2 on its own is a bootstrap sample from the same training data. Repeat that process with third data set and so on. So now you have multiple bootstrap samples from the same training data. And then you create your tree models. So for each one, now you can create a tree model. If you are doing classification, if you are working on a classification problem, meaning your response is a factor, like admit a student or don't admit a student, or if you are using that CTG data, then whether the patient is normal, suspect, or pathologic. So if you are doing a classification tree, then just pool all the votes and use majority vote as the final prediction. So for each data point, your final prediction will be based on majority vote from many trees now, not just one tree. Similarly, if you are using regression tree, so in Boston housing data, our Y variable is MEDV. So that's a numeric variable. So this is a regression problem. So we are using a regression tree. So in that case, you get average from model 1, you get average from model 2, average from model 3, and so on. And then you find the average. That becomes your prediction for each house. So that's what is called bagging. Now, if you use this approach and apply it to Boston housing data, and if you want to compare what happens with one tree and what picture will emerge if we do bagging, so now you can see your tree is basically these black dots. I don't know if you remember, there were like 1, 2, 3, 4, 5, 6, 7, 8. So there were 8 terminal nodes in our tree that we had in the last class. So each row, each line is one terminal node. And if you look at bagging, these red dots are based on bagging model. And you can see that red dots capture the actual data points more closely. And also like in between the two like gaps, so you are able to see predictions even between the gaps that we get with a single tree. So definitely like visually we can see there is an improvement. Another interesting thing that you may get as an outcome when you do bagging is that it also gives you some idea about variable importance. It looks at each variable and it converts the variable that is most important into 100%. So LSTAT in this case is the most important variable. And then compared to that, what is the contribution of each of the other variables? So for example, as far as Boston house prices are concerned, this variable is not really playing any major role when compared to LSTAT. And then these three variables are also quite low, less than or around 10%. But then you can also see two variables, LSTAT and RM. So they play a very significant role. And this we get not based on one tree, but now multiple trees. So these results are not going to change drastically if you split your data again or split your data slightly differently instead of 50-50, maybe 60-40. So these results are not going to change that much compared to what can happen with the single tree situation. And finally, if you do the scatter plot between actual MED value, so I have used the test data here versus the predicted value based on, this is based on tree. So you can see like compared to a perfect relation, how much variability you can see here. Similarly here, that variability is much less. So root mean square error with the tree model was 4.9 and root mean square error with bagging was 3.97. R square improved from 71% to roughly 81%. So 10% increase from tree to bagging. So that's a big jump. So whatever way you look at it, that's a big jump.
I had a question. On the previous slide, you compared bagging versus tree.
Yeah.
How does it compare to, maybe it'll be part of quiz or homework, but how is it compared to just a straight up linear or a multiple linear regression model? Does it work better or?
One thing is, this is just one variable LSTAT, and you can see that linear model will definitely require some pre-processing, or like before we can develop a linear model we may have to think about some transformations maybe, because clearly this is not a straight line pattern, it's not a linear pattern. So some amount of work may be needed in that direction. But I have not tried, but I remember that we did use this data earlier. So we may have to check, go back and check, but the comparison may not be very straightforward. And the other thing is a regression tree can handle nonlinearity very easily. Like you can see with bagging, these red dots clearly start to gel more comfortably with the original data, those blue circles, compared to what you will expect from a multiple linear regression model. But definitely that is something worth checking.
Thanks.
Coming to random forest, this method is similar to bagging, except there is one difference. And I will let you know very soon what is the difference. So again, we are starting with our big data, whatever we have, and split it into training and testing. And then we want to develop model or random forest model using the training data. We have to do bootstrap sampling, random sampling with replacement. So from the training data, we take our first bootstrap sample. Same process like whatever we did in bagging, exactly same thing. So you take your first sample, and then when you take your second data 2, which is second bootstrap sample, so again those data sets are independent of each other. Like what you get here doesn't impact health of data 2 in any way. You take data 3 and so on up to data k. No change so far. Like this is exactly same as what we saw with bagging. So in a way, random forest and bagging are somewhat similar till here. But what is different for random forest is this. So when you are constructing a tree from each data set, at each split, you take a random sample of your variables. So in Boston housing data, there are many variables like LSTAT, RM, ZN, and so on. So there are so many variables. So instead of using all the variables, we are taking a random sample to decide how splits will happen in a tree. This random forest, that name comes because of this type of randomness that is part of random forest algorithm. So because we take a random sample of independent variables while making the tree, each tree model at each split, so that's why it is called. So it is a forest. Bagging also is a forest because you have so many trees. But this is a random forest because you are using a random sample of variables. In bagging, we use all the variables. So when you are making a tree, you make use of all independent variables, not a sample. And some people felt that if we take a random sample instead of using all the variables, probably between training and testing, the gaps will be less. The chances that we overfit will reduce because we are taking random sample. But apart from that, everything is same, everything else is same. If we are doing classification, if we are doing classification trees, we take majority vote. And if we are doing regression tree, we find the average and use that as a final prediction for a given house. So all those things remain same. So in a way, actually, if you go back, in a way you can say bagging is a special case of random forest. So bagging is a special case of random forest. Why? Because when instead of taking a random sample of the variables, If you take all the variables, that becomes bagging. So instead of doing a random sample of like out of like 20 variables, you're picking up 5 or only 3 at a time. So instead of that, if you use all the variables while developing the trees, all these trees in the forest, you are essentially doing bagging. But if you are taking a random sample, then you are doing random forest. So that's the only small difference between the two. Everything else you can see is more or less same. In R, if you run this line called model lookup for RF stands for random forest. So it will tell you that random forest has one parameter. So it has just one parameter, and that parameter is mtry. It's labeled as mtry. And what is mtry? It's randomly selected predictors. So random sample of independent variables that we were talking about on the last slide, like how many, should we take a random sample of size 2, 3, 4, 5? So how many independent variables or predictors should we use? So that is actually the parameter that needs to be optimized. And random forest will automatically do that. We don't need to really worry about it because it will itself run various options and tell you that if you want to minimize root mean square error, if you are talking about regression, root mean square error is one of the performance metrics that we want to minimize. So for that, this mtry or randomly selected predictors, so it tries various options and then it is suggesting that the best value is 7. So this mtry for this data should be 7. So that's what it is suggesting. Another information you have is that this model can be used for regression problems. So Boston housing is a regression problem. So it is true. So it is just giving us information that yes, it can be used for regression. Yes, it can be used for classification. And yes, if you are interested in finding probabilities as a prediction, it can do that too. So it is just for information that what all things it can do. So with random forest also you can get variable importance, which may not be same as what we get with other algorithms. Simply one tree or bagging. So if you recall, in bagging, LSTAT was number 1. With random forest, RM is the most important. But these two were top 2 actually earlier also. They just switched this like place, but they are still top 2. So if you compare performance of tree versus bagging that I showed you earlier, so this is the same picture on the left. And then I also drew a picture for tree versus random forest so that we can visually see whether random forest is performing better than tree or not. So you can definitely see these green dots are trying to take the shape of that curve. And another thing you may notice is compared to like bagging. So for example, bagging, there's no prediction below this, below 10,000 line. But random forest also ventures more closer to even extreme points in your data set. And in bagging, you could see there's a like almost like a sharp line, whereas the scatter in random forest is trying to go towards even whatever actual data points we see. So it is exploring those things much more accurately compared to even bagging. And one of the reasons could be because of the random selection of independent variables. So that may be causing the results to be more realistic. So this is again with test data. And this is the performance of all the three models and how they are doing with the test data. So you have first one as tree model, and then second one is bagging, and the third one actually is the random forest. So compared to R square of 81% roughly, we go from 81 to roughly 87, 88%. So you can visually see the dots are scattered around this straight line more narrowly compared to other two plots. So bagging shows better results compared to the first one, and random forest is showing better results compared to bagging with the test data.
We had a question about how to compare the outcomes for random forest if the models are different. So I believe for like this, for each of the trees within it, how do you compare the prediction of each tree?
We don't do comparison of each tree in the random forest. We aggregate all the results because each tree is going to behave something like this. So we have seen that, like, if we create a tree model, what happens? So we know that slight change in the splitting can give you very different predictions. So what happens with one tree, how good or bad it is, we know that. So here we are combining the results into one number for each house. So each prediction now is estimate of MEDV for that particular house, which may be based on, like, default number of trees in the algorithm is 500. So it creates 500 trees. So obviously it is difficult to print 500 trees and see what each tree is doing. So we can get the result in the form of the performance, like, is it helping to give us a better prediction? And the answer is yes, because we can see that root mean square error has reduced from almost 4 to 3.3, and R square between predicted and actual values, like, these are complementary measures. Like, if root mean square error goes down, R square is likely to go up. So even if you look at just one number, you get a confidence that there is an improvement.
In the last homework, we have discussion on partition, 50-50, 80-20, things like that. So before doing bagging or random forest, the first step of partition also impact the model performance. So could you give some guidance, like what would be the best partition in the first place?
Yeah, so in this model, like I mentioned, that you have the complete data, and then you are splitting that data into training and test data of your choice. If you have a lot of data, 70-30 or 80-20, 90-10 may not matter that much. If you have a lot of data, and let's say it's a classification model, and your classes are balanced. So if you have like three categories, like normal patient, suspect, and pathologic, and if you have more or less like similar number of people in each group, which is unlikely, like with real data it is unlikely, but if you have that, most of the times these partitions may not have huge impact if you are doing random forest or like ensemble method. If you are doing a single tree, so it doesn't matter what you do, even if you do 50-50 again. So if you split your data into 50-50 and created one single tree, and you have one level of performance, and I showed you, again you create 50-50. Now I'm not talking about like different split, same split, second time with maybe another random seed, and your performance I showed you could vary like $7,000, which is a big number when the house price itself is 10,000. So much of variability. But when you are using random forest ensemble methods, at least that variability from split to split is going to be managed much better, because like random forest, if you have 500 trees and your average based on that is not going to change much. If you split it again 50-50 or 60-40 or 70-30, probably you can do experiment and have a hypothesis and see what happens. But my guess is that it's not going to change much, because like central limit theorem, if you take average of 30 values, so that normal distribution is already very narrow. So results of 500 trees, and if you are doing regression tree and you are getting average as a prediction for a house price, so I don't predict too much variability in that prediction. But if your classes, like number of classes, are highly skewed, where you have like 90% of the patients normal and 10% of the patients are like pathologic or have some problem, so it is highly imbalanced. If there's a like huge class imbalance, and there if you are dividing your data into 50-50, you don't want to have a situation where your test data, it has like all data from one category and hardly any sample from the second category, because that's a very rare category. So you may have to do your splitting, you have to maybe think in those terms also while deciding your splitting. You maybe do a table and see how many cases in the test data you get from each category, so that you don't have a situation where you have hardly any data from one of the categories. And usually for a given problem, if you are working for a company or government or anybody, so for a given type of data, if you have some experience with that, you will find automatically after like lot of iterations that maybe there is something that works with that kind of data very well. So I do not recommend whether you should always do 50-50 or always do 90-10 or 95-5 or 80-20. So nobody can tell you in advance, because it will depend on the data. But you can definitely explore. You can try maybe 3 different splits. If you doubt that splitting is going to affect your results very much, then use the example of that homework and try like multiple splits and see how your performance changes.
As you mentioned, unbalanced target variable result, it happens a lot in work. So does oversampling also applicable in random forest or other machine learning models?
Yeah, oversampling or undersampling you do before you come to a model, before you apply random forest. So that's called data preparation. So if you notice that there could be problems in my model because my data is like this, then you may have to do some work before you get your data ready. Just like you go for an interview, you have to get ready. So similarly, you have to prepare your data and make your data ready before some method can be applied. So random forest will not do it for you. You'll have to do it separately.
Okay, thank you.
Okay, no problem. So we created a random forest model. We saw the results, but many times like one thing people criticize about these methods, like these are machine learning methods. So one criticism is that they don't explain things. It's like black box. You don't understand what's going on inside. But of late, actually, people have been coming out with different methods that help to actually explain things more deeply. So one example I have provided here, which helps to explain individual prediction. So now you have developed a model and you are deploying a model or whatever you want to do with the model. So a new case comes and you apply your random forest model. It may give you a prediction, like it may say that, okay, for this house, the price should be $26,000. But out of all the variables in the Boston housing data, which variables contributed to that prediction, that you can get by making these kind of plots. Just as an example, so again, I use the test data, and this is the first case in the test data, and the model predicted, this random forest model predicted that the house price should be $26,272 for that house. And it also gives you some data on explanation fit. So that's like your R square. How much of variability is being explained for this house? So that's about 76%. And the blue ones are positive and red ones or red bars are negative. So what contributed to the higher house price in this prediction? There are these two variables, Zn being greater than 15.8 for this house and Lstat being less than 7.96 for this house. So they contributed to the higher house price, and RAD less than 2.6 and crime rate to little bit extent contributed to pull the prediction slightly down. But obviously the more weightage is by the first two variables, and that's why the price is high. But if you look at another case here, third example in the test data, prediction is 17,000. Now why this house price is predicted to be low? So the main contributor in this single prediction is the crime rate, which is more than 0.122. This one variable contributed to a lower prediction of house price and brought it down compared to a normal house. In this case, it is about 20,000, and Lstat being actually between these two numbers and RM being less than 6.08 pulled the price slightly low. So in a way, we see the results, we just see the predictions, but why that prediction is low or why that prediction is high. So these type of plots can give some insight about individual predictions. Because earlier insight that we talk about, like R square or root mean square, so those things are for the entire model level across thousands of houses, or like it's a big picture. It's not talking about the individual houses, but this one goes into each predictions and tells you slightly more than what you can get just by using that model.
Overall question, sorry, kind of related to the earlier question I had. How do you decide which one to go with? Or you kind of have to have all of these in your pockets and try them?
Yeah, for a given data, sometimes it may be difficult to predict what will work better. Sometimes it could be logistic regression may be well suited, or sometimes you may find random forest may work well. So it's especially with like huge amounts of data with all kinds of variables, it's anybody's guess which method works. But the idea is people want to have a method that is more accurate. So they try multiple methods and compare the performance and see which one they want to select finally.
Okay.
Yeah.
I guess I still don't really understand the justification for choosing random variables for the random forest. It seems like you're gonna get a lot of bad models that just randomly choose bad variables. Why would you want those for your analysis?
Yeah, it's just algorithm, and if you look at it in another way, so in bagging you are getting trees based on the same models, you are making multiple trees which may not be really very different from each other. So if there are some peculiar patterns in the data, or so all the trees are likely to be capturing same thing. But here you give a more chance. Your each tree is actually slightly weak, but together, especially when you are making predictions with test data, which is unseen. You have seen the example that I showed you. Random forest method improved R-square by about 7%. But I'm not saying that all data in the world will behave in exactly same way, where random forest is always better than bagging. But with this data, we saw it gives us better outcome. It finally boils down to like what kind of performance we can extract out of each model.
Okay, thanks.
Another method which is extremely popular, in fact, all the Kaglers, the grandmasters use it to win competitions. It's a method called extreme gradient boosting. So basically, the name given is boosting here. And what we do is we have all the data, we split the data into training and testing. And for the training data, we again create multiple data sets, just like we did for bagging, just like we did for random forest. Now your data one is same as training. So we are not taking Bootstrap sample now. You just use that data as your first data. And then what we do, the arrow goes here, we create a model, obviously tree model. So we create a tree, and the outcome of that tree goes back as a feedback when we are selecting the second data set. So this data set again actually is coming out of training data, but it comes out of, actually I should have maybe arrows coming from here also, because it is extracted from training data, but in such a way that while collecting data you learn from your mistakes. So especially those cases or those observations or those houses where the model went wrong, you collect more data, and where the model did well, you reduce the sample size. So you take like more samples in one category and less samples. So basically giving more weightage to one where you are making mistakes and you know you have to learn more, and less from where you are more or less comfortable that you are already doing well. So in that way, in the earlier methods, when we create trees, those trees are actually can be created in parallel. Even the data can be collected in parallel. But in this case, your training actually proceeds in a sequence. So you have to get your first model and see how it is performing with each house. And then you get your second data in such a way that where you are making errors, you oversample, and good cases, sample less. Again, create a model. Again, learn from your past mistakes. Again, have a new data set, which is obviously biased. You are biased towards each observation that you are selecting in your sample. Create a model. So this way, you get many trees. So this time actually your data 2 is not independent of the first data set. So it totally depends on what is the outcome of the model based on the first data, and then only you decide like how do I sample my second data from the training. So your final prediction in this case is a linear combination of weighted results from all the models, and that gives you like a housing price which it thinks that it will do a better job where earlier models may not be doing that well. If you run model lookup with XGB, XGB stands for extreme gradient boosting. you'll see that it lists 7 parameters. Unlike random forest, where it is actually, I would say it is one of the easiest to use to get a quick and decent outcome, where you don't have to struggle much actually to get a good model, because it automatically optimizes your mtry, which is the optimal number of variables you want to sample for each split. But extreme gradient boosting actually has 7 parameters that you need to like fine tune. Beforehand, we may not know like what will work, what will not work. But this model and these parameters also help us for regression models, for classification models, and estimating probabilities. So n rounds, for example, is boosting iterations. So it's like your data 1, data 2, data 3. So basically how many rounds you have. So in random forest, default is 500. Here I think the default is 100, but you can always like play with, you can reduce, you can increase. Another variable is maximum tree depth. So how big a tree you want, like what is the depth of the tree that you want in all those trees. So the chances are that if you create two big trees, like if your each tree is huge, then you may end up with like overfitting every time. So that could be a problem. So you may have to balance, like overfitting is not good, but underfitting is also not good. You don't want to have a model which is not able to predict. So you want to avoid overfitting, but you also want to avoid underfitting. But you can play with maximum tree depth. And then there's eta, which is like learning rate. So whether you want the model to learn slowly, or if you give a bigger value, it can learn fast, and so on. So minimum loss reduction before finalizing the trees, and so on. So you have like 7 parameters, and usually these 3 definitely are parameters that you want to experiment, change, and see like if you increase, is it improving the performance, or when you decrease, it improves the performance. So you may have to run it few times before you get the best outcome. So with extreme gradient boosting housing data, again LSTAT was number 1. So this is consistent with earlier models, like LSTAT is among the top. Random forest, it was number 2. And this time actually this is like a single biggest contributor, like second best is actually far behind. And there are some variables which hardly impact the performance. So this is like overall summary if you want to look at the final outcome of each method. When your model is performing at the R-square of about 70%, usually making a jump of like 10%, 15%, I would not say it is easy, but you can get it. But once you are like already very high, like 87, then every single percent can be very, very challenging. Those were the examples where we were looking at like regression trees, because Y was numeric. But in our CTG data, we have response variable of patients being normal, suspect, or pathologic. So obviously there we make use of classification trees. So we apply the same process. We'll see what happens. Just to recall, in CTG data we have 21 features or independent variables, and response is that the patient is either normal, suspect, or pathologic. So this is based on the majority vote of like 3 experts in this field, 3 expert doctors, and obviously they are in big demand, and sometimes they may not be available to look at a patient. So is there a way we can use a model to predict and classify a patient into one of the three categories. So that's the idea here. Using bagging, we got these results. So these are some of the top variables. If you are looking at top 5 or top 10, you can see. And then there are some variables that hardly contribute to the correct classification of a patient. With classification trees, we make confusion matrix, we calculate sensitivity, specificity, all those things. So those are our performance metric. And again, this is with test data. And you can see with a single tree itself, the model is doing really well, almost 91% accuracy. And sensitivity is best for categorizing patient as pathologic. So this model is like 98% accurate, but it's doing very poorly for suspect patients. Now bagging takes the accuracy to about 94%. So that's a clear improvement. And sensitivity is higher for class 1, so about 93% to 96%, 3% improvement, and slightly higher for class 2, 73 to 75 or 75.5, and 98.7, 97.8. So this has gone slightly down, but overall accuracy has improved slightly. Now coming to a random forest model. So just to again give a slightly more insight into random forest. Random forest, they are developed by aggregating trees, can do both classification and regression, and they avoid overfitting because we depend not on one tree but many trees, and then with the test data the results are likely to be more consistent. So that way they can overcome overfitting, can deal with large number of features. So many times, like I have seen people asking me, I have so many variables, but most of the variables are factor variables. What should I start with? Like which method we should try first? So whenever I come across that situation, I always suggest them go with random forest. Helps with the feature selection based on importance, and it's also very user friendly. Although like some packages, they ask you to like optimize two free parameters, like one is number of trees, so you can play with whether you have 500 trees or 100 trees, but default 500, you will see that you will rarely get a chance to really play with it. 500 works fine. Most of the times even 100 tree is good enough. But the key parameter is variables randomly sampled as candidate at each split, your mtry that I mentioned earlier also. And if you are doing classification, so usually this mtry typically is square root of your p. So if you have 16 independent variables, you take square root, you get 4. So you use like 4 variables, sample of 4 variables at a time at each split as maybe starting point for mtry. So that's good enough, and then you explore whether you want to increase it, decrease it, and what happens to the performance. But if you are doing regression, typically they divide p by 3. So if you have 30 variables, for example, divide by 3. So you take a sample of 10 every time. But let's say hypothetically, like this doesn't happen, but like with 5 trees, we cannot create a forest. We need more trees. But assume that your forest has only 5 trees. So this is the first tree, this is the second, third, fourth, and 5 trees in this forest. So how this random forest model predicts? So now you have a new patient data. You created a model, you have a new patient data. For example, first tree ALTV is 30. 30 means I go to the right because this is more than 16, and there I encounter a variable mstv, this one. So this one is 0.2, which means I turn this side and I end up with this terminal node, which says that the prediction should be 2 because that's the highest class. So this is the prediction. So that's not the final prediction, but prediction of one tree in the forest. Second tree tells me that start with dp. So this is my dp, and the value is certainly less than this. So I go to this node and look for altv, which is 30. So 30 is less than 68, so I go here and again look at altv, which is 30, but this time I go this side because this is more than 8, and then it says look at astv. So astv is 80, so 80 takes me to this node. Now again, second class, the probability is the highest, so this tree also predicts the patient to be suspect, class 2. We do the same thing here. dp, this one takes you left, altv takes you this side, mode is 10 less than, so you end up with this node, and I can see that the third bar is the highest, so that's the probability. So the prediction is for 3, that patient is pathologic. Fourth tree of the forest starts with dp, so we go left, altv 30, we go left, altv 30, we go right and reach terminal node, and the prediction is that the patient is suspect. You do the same thing here. You go left, altv 30, go left, altv 30, go right and look for uc. uc is 0.1, so you end up here. So fifth tree tells you that actually this patient should be normal, category 1. So now you have prediction from all the trees in the forest, this small forest, hypothetical forest. So you have 2, 2, 3 times, and 1 time category 3 and 1 time category 4. So majority class is 2, and we can say that this patient is suspect. So the prediction is that the patient should belong to suspect category. But when you run the model lookup for random forest, I have shown this you earlier also. So same thing for classification trees. This is your parameter, and this parameter tells you that mtry should be, so it is trying to maximize accuracy. If you notice, y-axis for classification tree is accuracy. So looks like this is 11, a sample of 11 variables at each node out of 21, if you recall. Now for random forest, for classification tree, when you look at a variable importance plot, so it gives you a breakup for each class. It gives you for normal, suspect, and pathologic. So for each class, it tells you which variables are playing an important role. So which variables are playing important role for a normal patient, a suspect. So for example, ASTV plays the most important role for a suspect patient, but less important role for a normal patient. So this variable doesn't contribute as much for a normal patient as for suspect. Yeah.
Could you introduce the importance, how the concept and how it's calculated?
When you are creating a prediction model or classification model, we are not including all variables in creating a tree. We are taking a sample, so some variables are not there. for each tree. The algorithm can find out in what all cases this variable was present, in what cases it was not present. Let's say if a variable is not present in creating a model and your performance is 90% accuracy, and when that variable is present, still your classification is 90% accuracy, so that will mean that that variable may not be important, because whether it is there or not there, it doesn't affect anything. But if you have a variable, when it is present you get 90% accuracy, but from whenever it is absent, on an average you are getting only 40% accuracy. So that's a very clear indication that the model is missing that variable. So that's how you can judge like importance of each variable. Like in this case, random forest, you are not using all the variables all the time. So that gives you a hint, and random forest can automatically do all the calculation and tell us that whenever it was missing or present, how much impact it had on the model in terms of correctly classifying patients. So that's the idea behind variable importance plot.
Would you use this variable importance plot to like prune variables, like to just say, well, these ones across the three classes don't look important, like tendency, so I'll just remove it from my model and retrain?
Yeah, so those variables which are not important, basically because they are not contributing in whether they are present or not present, things don't change much. So you can make your model less complex. If it is patient data, for example, I'm sure for collecting data on each variable, that hospital or whoever is collecting data, they may have to make some measurement or do some testing. So they can reduce the cost if they can eliminate, or if you don't create a model that has unimportant variables. Actually, in that sense, random forest is also used for feature selection. If you want to select like what variables I should use in the model, not only for random forest, even for extreme gradient boosting or any other method, it can give you like, okay, these are the variables, they are not playing a role, so just forget about them.
Thank you.
Yeah, no problem. So this is the comparison. If you also include random forest to the list, 0.939 improves slightly to 0.9455, and at individual level also we see some improvement. Like I can see class 1 sensitivity slightly up, class 2 also up, but class 3 slightly down. And you can see that in the confusion metric also. There was a huge misclassification for class 1 in the tree, and bagging actually brought it down. So 26 plus 30, only 30 compared to what we had here. That's where model was not performing that well. And in fact, even here, 29 and 7 misclassified for category 2. So that reduced slightly here, but this one is still maintained. This one reduced with random forest, but this one almost unchanged, 29, 29, and 30. So those patients seem to be very tricky, who were classified as suspect, but model continues to predict them as normal. Now with extreme gradient boosting, if you look at variable importance chart, so frankly speaking, there may be some ups and downs in terms of the top and bottom ones, but it will be very rare that something which is at the top in random forest or bagging goes towards the bottom in another method. So that's really unlikely to happen. But at the bottom level, for example, they may shuffle around. They have such small impact, hardly an impact on the model. And sometimes just because of sampling fluctuation, they may go slightly up, slightly down. but still they are not of much use. But if you look at top 5, these are top 5. If you have interest in top 10, then you see top 10 somewhere here. And this is the final summary of all 4 methods. Bagging we can run as it is, random forest we can run as it is, but extreme gradient boosting, I showed you like 7 parameters, and especially like those 3 parameters, they need to be like tried, tuned. So you may have to do like go up, down, explore. You may not get result immediately, so that's why that's something one has to make some strategy, like how do you want to do it. But you can see there's a slight improvement, 0.1%. So I'm going to run this. So this ML bench, machine learning bench, actually that has Boston housing data, so I'm using it for that. So you run that, and I like to use a smaller name so that we don't have to type much. So Boston housing is very long, so we'll use my data. And while splitting, just so that all of us have like same training data and same test data, just for repeatability, I'm using a particular seed. We take 2 independent samples and we are doing 50-50 split. So if I run this, we split the data roughly into 50-50. It's never exact, like training has 262 but testing has 244. But what happens is if I repeat this, I still get same number here because exactly same observations will be part of my training and test data. If I use another set.seed like 234 and run this, you can watch test and training numbers change. You see 252, 254, so it can change. Keep it 1, 2, 3, 4 so that my result, what I show you on the screen and what you have on your computer are exactly same. Actually, for doing all the tree models, whether it is the regression or classification trees, I'm also going to do cross validation that we had done actually much earlier. So I'm bringing it back here. And the way these cross validations occur, so if you say number is 5, that means it breaks the training data into 5 parts. And if I use the same seed, so again it will do that in a similar manner for everyone. So that's the only reason I'm using a set.seed here. We'll do 5 cross validations and we are doing repeated, so let's repeat it 2 times. We don't have to do by hand, we are using computer, so why not repeat? And then it also allows you to do in parallel because the data separation in bagging or like creating models don't have to move in a sequence because that can take a lot of time. You can do all that in parallel. Let's run this too. And then for making the models, right now I'm going to do regression tree because it's Boston housing data. If you simply type str my data, for example, in console, it can tell you that we have these many observations and 14 variables. MEDV is our response variable, it is numeric, so that's why we are doing regression trees. So the data we are going to use is train, response is MEDV, and I'm just putting a dot to indicate I want all independent variables. And if you recall, I had this variable importance plot. So if you want that plot, you'll have to say true here. If you don't include it, then if you try to plot variable importance plot, it will not have data. So make sure this is there. So simply run this. and it will do bagging for you. So you can see it hardly takes any time. If you want to know what is inside bag, simply like select bag and run. So it gives us some information that it is doing a bagged classification and regression tree with 262 samples. So that's your training data. You see, you have 262 observations. And in our data, we have 13 predictors, x1, x2, and so on. We have done cross-validation 5-fold, and we have repeated 2 times. And these are the sample sizes. So when you split 262 samples into like 5 parts, 4 parts will have 209, and the 5th one is reserved for estimating error. And then next time, remaining 4 and 1 reserved for estimating error, and so on. This is only training data. So training data gives you root mean square error 4.7, R-sq about 74%, mean absolute error about 3.206. You can do the variable importance plot. It says that LSTAT is the most important variable, and so on. Now we can use this bag model and use the predict command with test data, and instead of using a very long name, I'm just using a short name ba. So those predictions will be stored here, and then you can make a plot that I showed you in the PowerPoint. So it's just a scatter plot between predicted value and actual value. And if you calculate square root of mean of actual minus predicted whole square, so that's what gives you root mean square error. And square of the correlation between two is nothing but your R-sq value. So those are the values I used in the plots. If you want to run random forest, exactly same setup. The only thing I change here is method. So method now is RF, random forest. So select and run. When you run this, it says one package is needed for this model, because Caret is a general package for running machine learning algorithms. And if you want a specific package, it may need to be installed. So one package is needed. Would you like to try to install it now? So for selection, you can say 1 and hit enter. It will install that. Now if you try to run, it should run fine. Give it some time. It may take few extra seconds. So it is done, and then if you click on forest, double click on forest, and you want to see more, so it says it used random forest on 262 samples, 13 predictors, and same thing, cross validation. And while doing random forest algorithm, it tried different mtry values. So it tried various values, and it says that this is the best. mtry 7 is the best. So that's what it reports. And it also tells you that root mean square error was used to select the optimal model using the smallest value. So unused data, like data points that were not used for one particular tree in a forest, are being used for estimating the errors. Run this line, plot variable importance. You can also try plot forest. It uses root mean square error on y-axis and then tells you that this is the smallest value. That's why this is the optimal mtry. If you want the actual numbers, you can ignore the plot and simply type or select variable importance part and run. It will give you those numbers that were used for the plot. You can do forest $. So let's find final model. It has a lot of information. You don't need to look at everything, but just to give you some idea. So forest $ final model. If you run that, it gives you the type of random forest it did was regression, because MEDV is a numeric variable. How many trees in this forest? 500. And number of variables tried at each split? 7, because that was the optimal. And percentage variability explained, like R-square, you get about 81.32. And mean squared residuals, so this is mean. If you take square root, that becomes root mean square error. And you can do similar things, like you can predict for test data and plot that scatter plot that I have been showing you. You can calculate root mean square error, R-square, based on test data. And this was the interesting part that I showed you in the PowerPoint, where you can explain predictions. So this is the test data, and I only want to look at like first 3 just to give you idea, but you can do it for every house. So these are 3 houses. First house in the test data, 7th one and 8th one. They have all these values. So what it does is, to explain, it takes a continuous variable, like let's say LSTAT, and you can specify how many bins you want to group a continuous variable into, so that we can explain something. Default is 4. I have increased it to 5. So if you run this, it creates explainer, and then here I'm saying that I want to explain this prediction with 5 variables or 5 features. So that's why 5 here. So we run that, and then you can plot it. So this is the plot I showed you, which can give more insight. Instead of just getting some output from the black box that your prediction is $26,000. So why? What is contributing to it? If you look at top 5, so other 3 don't really play any major role, but first 2 definitely tell you that this house has a high price or predicted price because ZN is more than 15.8 and because LSTAT is less than equal to 7.96. Now you may wonder what exactly it means. You can always put a question mark and type Boston housing to understand what that variable is. So ZN is proportion of residential land zoned for lots over 25,000. So if that value is less than 15.8, it helps to increase the value of the property. Now look at this lower prediction for case 8. Crime is more than 0.12. So let's see what it means. So crime is per capita crime rate by town. So if per capita crime rate is more than 0.12, that's what has contributed to lower the price of this house. So predicted price is house because of this one major reason. So that way you can explain, like in this case there are 5, but if you see a situation where more variables are explaining a prediction, then you can always go to 10. You don't need to have this 5 here, you can go to 10. You can also do the same plot in a slightly different way. It's called plot underscore explanations. And we have to put explanation there that we used in the previous one, this one. So same information can be provided in a slightly different way. So for each house, it lists all the features or variables. For example, for house number 1, the two blue ones, how they are playing a role, and also like indicates other variables that are not playing a role. So especially if you are looking at maybe a lot of 20, 25 houses in a region, this plot may be easier to interpret because it can give you a complete picture in one snapshot. So then we jump to boosting, and you'll see that the structure is similar except that under tune grid, you remember I mentioned that it has 7 parameters. So we list everything, but usually what I do, I play with just these 3, but one can like explore that also, because you never know, with different data sometimes something may work in a different way. For example, here I'm using maximum depth, like how deep the tree should be. I'm just saying that it should go 3 levels. Default in R is 6. Default is 6, so I have actually made a smaller tree while making these boosted trees. And learning rate default is 0.3. So there also I had slowed down the learning rate slightly. And gamma default is 0 actually. And gamma is typically used for avoiding overfit. So if you are seeing like lot of difference between training and test data, so gamma is the one you can go to. So 0 means you are not addressing overfitting. It may not be needed. But if you find that there is overfitting going on, like training is improving, training performance is improving, but test performance suffers, so that means there is overfitting. So in that case, you can try to increase gamma. Higher the gamma, it will bring training and testing performance closer and closer. So basically avoids overfitting. But you will be fine if you explore these 3 and experiment around these 3, because trying to change all 7 will be very challenging sometimes. So I'm going to run this. So one package, so XGBoost is not there, so let's say one install. So it installed the package and now it's running the codes. You may see some warning messages, but in R, warning is okay. You can keep on ignoring warning message. So this 21:06:11, that's time somewhere. Definitely not Boston time. Okay, so now it's run. Then you can run the variable importance. So this is the same plot we got earlier. And similarly, you can run predictions and the scatter plot that we have seen, root mean square, R-square very easily. So now coming to classification example that I gave you. So under files, I think you should have ctg.csv. So it should work fine. If not, you may have to upload it. So run this and read it into my data. So if you look at str my data, so it has 2126 observations, 22 variables. NSP is the response, but it should be factor, because if you put integer, then automatically it will treat this problem as a regression problem and try to do regression tree. So make sure you convert it into a factor, because it is a factor variable, so that it uses the correct method. So I have done that in this line, and then the standard splitting, and then let's use 2 here also just to be consistent, 5 and 2. And then you do your bagging, importance, so that's the plot, and then predict and do the confusion matrix. So I showed you a part of this matrix. Now random forest, same process. So for random forest, number of trees as a default is 500. And then if you plot the variable importance, so the only difference for random forest is that it does variable importance for each level, unlike bagging and extreme gradient boosting. And then predictions and confusion matrix in the standard way that you have done earlier. And same thing with boosting. So boosting, I'm saying number of rounds 500, so almost saying that I want 500 trees. It creates one tree, gets the feedback, then takes a new sample, and then again creates a tree, uses that feedback for the next sample, unlike bagging and random forest. So whenever things happen in series, it takes more time. And when things happen in parallel, they are faster. So this might take slightly more time than random forest as well. So while it is doing that, another thing that you can do, like when you're plotting the variable importance, let me add a line, and variable importance, I'll just denote it by V. So let's say that has variable importance for the boosted model boo. Then we can say plot this V, and I want only top 5 instead of like everything, because sometimes you have a lot of variables. You don't want to see the whole list. Like if you have 80-90 variables, you don't want the entire list. So you can say maybe 5 or 10, whatever you want. So that will plot only 5.
Professor Wright, could you take this time to expand on how ROC curves are addressed for these types of modeling techniques?
So ROC curve is relevant. They are not relevant for obviously regression trees, because that's there you have a numeric variable and performance metrics are different, like root mean square error, and so they are relevant for classification type of problems. And usually the concept is more for binary situations. And by binary, I mean where response variable has only 2 values. Like a customer will accept credit card offer, or the customer will not accept credit card offer. Or insurance, for example. So somebody will accept insurance offer, will not accept. And in classification problems, I have seen a research paper where they estimate that 80% of the classification problems fall under binary situation where response has only 2 values. So ROC curves are meant for those situations where you have 2 values. When you have actually more than 2 values, like 3 classes, 4 classes, sometimes 10 classes, then ROC may not be the best way to compare models, because it can get tricky and like confusing, but it definitely makes huge sense with 80% of the classification problems where response has only 2 values. Does that answer the question?
Yes.
Okay. So I was talking about your variable importance. If you don't want to see like everything, just the top ones, you can always say plot 5 or plot 10. So it will do that very easily. And predictions and confusion matrix, you can do it in a standard way. This requires more experimentation. I have some values here, but that doesn't mean that for all data these values are going to work. So you can remember that this is a learning rate, And when learning rate is lower, that means your model learns slowly. So that also means that you may need more rounds. So sometimes, like if you want your model to go like too slow so that you can capture maybe the optimal levels, then parallelly you may have to increase your number of rounds to give it a chance, because things are going to improve very slowly. And if the number of rounds suddenly are over and it has not done even like half best of what it could do, so you may have to increase number of trees. You have to create a bigger forest. But if your learning rate for some data like even higher value works good, then number of rounds could be just 100 or even sometimes less. And then maximum depth also can affect both actually overfitting. If you have very deep trees, then you tend to overfit, because then you are going deeper and deeper into the same data, training data, and that can also cause overfitting. So it is a balance, like you have to balance overfitting and underfitting and see what works for you. But with that, actually, I'm going to stop here. See you. Bye-bye.
Thanks, Professor. Good night.
Thank you. Good night, guys.
Thank you.